All right, so now we're going to be talking about variance and standard deviation. When we talk about variance and standard deviation, it's really more like, in that conceptual example, that distance away from the president, where we're looking at the actual distance, right? And in statistics, what we call distance away from the mean, the president in this case, is a deviation. We call that a deviation, right? And so what we might want to do is get sort of the average deviation, right? But there's going to be a little bit of an issue. When we get the deviations from the mean, remember the mean is sort of the middle, the value that's in the middle, right? So the amount is actually sort of in the middle of all the other values, right? Some of the values are going to be greater than the mean, and some of the values are going to be less than the mean. When we add all of those up, right, the formula looks like this. So the summation sign, where we take each value in our distribution, x sub I, and take out the mean, so subtract, get that distance away from the mean, that deviation from the mean, right? When we add all those up, where I goes from 1 all the way to n, however many we have in our sample, we basically get 0, right? Because sometimes the value is greater than the mean, sometimes the value is less than the mean. When it's greater, the number is greater than 0. When it's less, the number is less than 0. You add up a whole bunch of positive and negative numbers, you end up getting something very close to 0. So that's the problem, because when you get 0 as your sum and then you divide by whatever your n is, no matter what your n is, it's going to be 0, right? Because 0 divided by anything is 0. And so this is not going to work for us, right? That's not going to be good to have every single average deviation being 0, right? That's not useful. So what do? Here we're going to sum the squared deviation. So instead of just summing up all the deviations, we're going to square the deviation and then sum those up, right? And whenever you square it, you get a positive number, right? So the sum of squares is always going to be positive. And you get many advantages out of doing this squaring business, and we'll learn more about some of those advantages later. But let's talk about how to write this in notation. So here we have that same idea, that same deviation idea. We're looking at distances away from the mean, right? But we're going to square each of those distances, right? I equals 1 to n, right? Now, just a word about this summing notation. Basically, when you have this summing notation, whatever's here, you need to do this first and then sum up everything in here okay? Sometimes what people do is they sum up all of x sub I first, right? So they sum all of them up and then subtract out the x. But we're not summing the values, we're summing the squared deviation. So you got to get the squared deviation first, right? And each value is going to have a distance, and each of those distance needs to be squared, and then you need to add them up, okay? And then this won't equal to 0 unless all your values are 0 and your mean is 0. But barring that case, they won't usually equal to 0. All right, and this is going to be called sum of squares. And that's often shown by using the term SS, right? And if it's sum of squares of the sample, sometimes you'll see this notation where it has a little x down there. If it's the sum of squares of the population, which you probably won't ever have, it will be SS sub big X, uppercase X. All right. Now we could look at the average squared distance from the mean, average squared deviation, right? And you do that simply by dividing by the number of values you have, right? So when we have the variance of a sample, that's going to be called S squared. That's going to be the variance, right? I'll write it in blue, right? So that's the variance of a sample. That's just going to be SS divided by n, right? Now, the problem with variance is that it's not in the same units as your mean because we've squared all the distances, right? So in order to bring it back to the same units as the mean, it's easier for comparison, what we're going to do is get the standard deviation by just square rooting each side, right? So standard deviation is just S, and that's going to be just the square root of variance. Ta-da, right? So standard deviation is now just the average distance from the mean instead of average squared distance away from the mean. Now, this is going to be for samples, but in order to get variance for the population, they use the lowercase sigma. So for variance, it would be lowercase sigma squared, and for standard deviation, it would just be lowercase sigma. And I'll show you in a little bit how to do that. All right, so now let's take a little bit of time to talk about sum of squares in depth, all right? And before that, there's a little typo on this page, so I'm just going to correct that so that it'll be smooth when we get down here. All right, so let's start from the beginning. Sum of squares is always the sum of squared distances away from the mean, right, of the sample. And the mean of the sample is x bar. That's how we denote it, right? That's the symbol for it. Now, the sum of squared distances away from the mean is going to be the smallest sum of squares than from any other point. You could pick any other number, right? This will give you the smallest sum of squares. Any other number will give you a bigger sum of squares, right? Now, here's the problem. The sample mean is rarely ever the actual population mean. And because of that, the population mean is this any other point, right? It's any other point. So if we had the real sum of squares from the population mean, we'd actually get a bigger sum of squares than we actually have, right? That's a problem. Here's why. Because then that means because we have a sum of squares that's a little bit too small, our sample standard deviation is going to be actually a little bit smaller than our population standard deviation all the time, right? That's an issue. We're always sort of undershooting the population standard deviation. So to correct for this, we're going to divide the sum of squares from our sample by a slightly smaller number than we actually do. Remember, right now, to get S, or standard deviation, we take sum of squares, divide by n, right? That's what we do right now. Well, this won't help us approximate the actual population, right? And so here, we're going to need to divide by a slightly smaller number. Because when we divide by a smaller number, then our resulting answer is slightly bigger, right? So dividing by 5, you're going to get a bigger answer than if you divide by 8, right? And so because of that, we're going to use that. So instead, in order to approximate the population, standard deviation, right? What we're going to do is use SS divided by n minus 1, right? Because this is going to be a slightly smaller number, giving us a slightly bigger population standard deviation, right? And why n minus 1? Why not n minus 0.5 or n minus 2, right? There's a proof that you could look up online called Bessel's correction proof, and it's a really elegant proof if you have time to look it up. All right. So that's my spiel on sum of squares, but we'll probably come back to this because it's a pretty important idea. All right, now let's talk about the difference between population standard deviation and sample standard deviation. Now, we always want to make inferences from the sample to the population. That's what we really would like to do. And our sample distribution is denoted by lowercase x. Our population distribution is denoted by uppercase X. And we're always going from in order to make that leap, we're going from sample statistics, right? This should say statistics to population parameters, right? And so we're going to be estimating things like estimating mu from x bar, right? That's estimating the mean of the population from the mean of the sample. And we're going to estimate the sigma, or the standard deviation of the population, from S, which is the standard deviation of the sample, right? So sigma is sort of a new notation. Notice that for population, we're using parameters that use Greek letters. And here we're using regular Roman letters. All right, so now let's talk about the formulas for these. So remember, when we talked about mean, mu in this case, and x bar in this case, we talked about adding up all of the lowercase x's and dividing by lowercase n. Here, we added up all the ones in our uppercase x's and dividing by uppercase n, right? So just superficial changes, right? When we talk about standard deviation, here we're going to be talking about sigma, lowercase sigma, or talking about S. All right, so let's actually write down this formula. You could write it as square root of sum of squares divided by n. That's one way to do it. But one thing you could do is sort of think about double-clicking on this, right? Right? Let's say I double-click on it. Then what we would get is you'd see the whole shebang inside. Hopefully I could draw it. Sum of squares really means give me all the square deviations, distances, away from x bar, square all those. And if you want, you could put in I equals 1 all the way up to n, right? Lowercase n, right? All divided by n, right? Or if we want to actually estimate, use this to estimate that, we would divide by n minus 1. This is an uppercase S, and I'm going to denote that by using like a little bar there. In order to have this estimation, we would use lowercase s. Lowercase s. It looks just like uppercase s, but I'm not going to put that little handle right there. And in this case, what we would do is divide our sum of squares by n minus 1. And that's our way of estimating from S to sigma, right? That's our estimate. When we talk about the population standard deviation, it's still SS divided by n, but it's uppercase N this time. And when we sort of double click on SS and see what's inside of it, right, we unpack that. Here's what it looks like. It's big X sub I minus mu this time, squared, all divided by uppercase N, right? So here are all these formulas. We have formulas for standard deviation of the sample, standard deviation of the population, but we also have this new idea. This is sort of in between this one and this one. It's a way of going from sample information to estimating a population standard deviation. Now, usually we don't calculate sigma directly because we don't have every single value for the population. Usually we calculate small s, which is going to be the estimated standard deviation. And we hardly use this one as well because we don't really care about the standard deviation of just our sample. We really want to know the standard deviation for the population.